All right, we're going to do Chapter 8, number 49. And in this case, it says, in an old-fashioned amusement park ride, passengers stand inside a 5-meter diameter hollow steel cylinder with their backs against the wall. So we have a cylinder like this. That's spinning about the center. And the people are standing against the wall. And then you spin the whole thing. Okay. And it's a 5-meter diameter, so we got to have the diameter. In fact, we don't care about the diameter. So the radius is 2.5 meters, half that. Then the floor on which the passengers are standing suddenly drops away. If all goes well, the passenger will stick to the wall and not slide. Clothing has a static coefficient of friction against the steel in the range of 0.6 to 1, and a kinetic friction coefficient in the range of 0.4 to 3. The sign next to the entrance says no children under 30 kilograms allowed. What is the minimum angular speed in RPMs for which the ride is safe? So we want to find omega in RPMs. Now we have to think about this because they give us like 4 different values for the kinetic friction. For the kinetic and static friction. Which one would you actually solve for? Well, ideally, if you're making a ride that humans are going on, you want to make it absolutely safe. So you want it to work no matter what the lowest coefficient of kinetic friction is. If you do the lowest static, that works as long as they don't move there, but what if somebody pushes them, then they would start to slide and they would slide off the wall. So you want them to not even move if they're on the lowest one. So I just look at it and say, okay, which is the smallest kinetic frictional coefficient, and I'm going to solve for that one. So I'm going to use the one at 0.40. So I'm going to use this one. I want the person to stick on the wall even if they start to move or slide or anything like that. They'll still be stuck on the wall. All right, so we're going to do a free body diagram for the person here. So we have mg here, but now the normal force is coming out away from the wall. Remember, you're pinned against the wall. And what keeps you from sliding down is the friction force. So that's your free body diagram. And actually, kinetic friction. Again, we're going to make this our axes. This is x. This is y. So I'm going to do F net x. And it's going to be equal to minus the normal force. But that's the direction you're going in a circle, and you're going to the left because I drew the guy over here. So this is going to be minus mv squared over r is equal to minus n. Or mv squared over r is equal to n. But we can't solve that because we don't know what n is, the normal force. So let's see if we can figure out the normal force by doing F net y. Now at F net y, we have the friction force, positive, minus gravity. Okay? And we don't want them moving up or down. That's the whole goal, is that they're pinned to the wall. So this is going to, we'll move this over here, and kinetic friction is just going to be equal to mg. Remember, kinetic friction is equal to mu sub k times the normal force. And then the normal force is going to equal to mu sub k, mg, divided by mu sub k. If I'm just solving that for the normal force. Now I can plug this back into here for the normal force. And I'm going to get mv squared over r is equal to mg over mu sub k. What am I solving for? I'm solving for v. I want to find the velocity. Once I get v, I'm going to convert it to omega. So I'm going to solve this. Now remember, notice that when I divide by m, the m's go away. That whole sign of you can't be under 30 kilograms is irrelevant. It doesn't matter what your mass is. It'll work just fine for any mass. Okay? And we're going to solve this for v. So we're going to get v squared is equal to gr over mu sub k, or v is equal to the square root of gr over mu sub k. So I'm going to bring this over here because I'm running out of room. So V is equal to the square root of 9.8 times the radius, which is 2.5, divided by 0.4. And you take the square root of that. When you do that, you get a value of 7.83 meters per second. But we want omega. And if you remember, V is equal to omega R. So omega is equal to V over R, or 7.83, divided by 2.5. And when you do that, you get 3.13 radians per second. However, they specifically asked for it in RPMs, revolutions per minute, so we got to convert this. And we have 2 pi radians is 1 revolution, and that 60 seconds is 1 minute. So if I multiply by 60 divided by 2 pi, I get omega is equal to 29.9 revolutions per minute, or 30 with 2 sig figs. 30 revolutions per minute. So, what's that mean? Well, 30 revolutions per minute is pretty obvious. You're going to do a revolution every 2 seconds. So every 2 seconds it'll take to go around. And then everybody will be stuck on the wall. You've probably gone to one of these amusement parks. They have variations of these. They used to have one that they called the Roundup. I used to go on it when I was younger. Now I go on it and I just get sick. But it would spin like that. Once you're stuck to the wall, they would actually tilt it. So it had to be spinning even faster than this, so that you were pinned to the wall even when you went vertical. Remember, this was just saying that the kinetic friction had to be greater than gravity. And so you have to have more if you're going in a vertical thing. You have to have that square root of RG to get the minimum velocity so everything just sticks. So there's different variations of that, but that's how it works. All right, good problem.